Okay, we are almost coming to the end of this chapter. We are talking about probably the most famous or commonly used random variable, the normal distribution. And so what we are going to do will be something like this. But this is just this is not entirely related to normal distribution, but is for any continuous random variable, and small f is probability density function. So if I plot it like this, just to exaggerate, this is not a normal. So this is the small f. Your big F of x is to give you the area once or x is fixed. So this is the area under the curve. And this is the left or the lower tail. All right, so because we see from minus infinity to here is the lower part of the tail, and this part is the upper part. So this is what it is. And now we wanted to define a quantile. And the quantile is lying between 0 and 1. All right, and so basically, the question that we are asking is the reverse. I still have the same curve, all right? But now I insist that this area equal to Q. And what I'm interested is, what is this number? So in a way, the two questions here are inverse of one another. Here, you choose your x here, and then find the area, whereas the quantile is basically solving the equation so that this will give you back this. So for the time being, let us use x sub q. In our slides, we use z, but that is basically a common notation for normal distribution. So basically, what we are looking for is a number, xq, so that this is q. So if you accept this our notation is the inverse of a function, then you are basically calculating this. So basically, you are calculating the inverse of a function. Now, if you have a closed form formula for the distribution function, then it would be just a matter of solving the equation. For example, when x is exponential of parameter lambda, then this is f of x is equal to 1 minus e to the power minus lambda x. So if we want to find out the f inverse of x, so let's for the time being call it y. So we are basically solving this equation, 1 minus y, and then move the e to the power minus lambda x to the other side, and then I take log. Now, all the log here is natural logarithm with base e, but if you really want to emphasize it, this is e here, all right, or ln, and so this is minus, and you divide by lambda, and that would be your x here. So this would be our the inverse function, all right. Okay, we call it y here. Okay, so if you have a Q that you're interested, say, let's say the 90 percentile, so you want to find out what is the number that corresponds to the top 90%, then you just do it this way. Now, why we wanted to talk about this for the normal distribution has the main disadvantage that the distribution function can't be written as a function. I mean, in what the jargon that we use is we cannot write it as a closed form. I mean, just one function expressions. And so as a result, we can't really solve it. All right? So numerically, what people do is for the normal distribution, let's say this, they are interested in the set Q, e to the power minus t squared over 2 dt. So what people do in the past is sort of by trial and error, they fix, say, Q is 95%. All right? And then they just have to try by trial and error. Now, of course, there are a little bit more sophisticated method, like Newton's method and all this. So basically, you want to solve an equation. So basically, we want to solve this equation. And it has this kind of different techniques of solving this has been around for long time. I mean, even before Newton's way. Another way is to, basically give yourself a good estimate of the upper bound, and then use a bisection way to basically sort of clean it up. All right. So, but people have done this long ago. All right. And so this is before the calculator is very popular, and computing power is keep on increasing. I think you probably will know my age if I tell you this. When I was in Set 3, I started to use calculator, but calculator was very, very expensive. Just the usual one that you see in the shop, I mean, with percentage and just plus or minus. That is over $1,000 in Hong Kong dollar. Now, so as poor student, I use slide rule. I don't know whether you heard of it. You might want to Google it and look at the image. Then the calculator price came down in when I became Set 4 because Sharp and I think some other Japanese company came up with more powerful calculator and also at a more reasonable price. For O-level or A-level, we were not allowed to bring calculator, so that was the age there. Now, of course, the problem is now getting less and less, and I've told you the early days of statistics software, the software is basically in storing the table that people have computed earlier. And so when you ask for certain things, then they just go back to the background and then look up for the number for you. But now I think a lot of this calculation is real time. You ask for it and then they just calculate for you because there are the computing power plus some little math trick here and there enable you to do so. Now, why do we look at, so we are looking for this. All right. So it is sometimes of interest to look for quantiles of the normal distribution, like the following example. Now, this statement is a little bit, you don't take it very absolutely seriously because we are actually of interest to look for quantiles of any distribution, not just normal distributions. In fact, we'll be interested in the quantiles of T distribution and chi-square distributions and some other distributions. What we are going to do now, of course, during your study or your usual work, you can use whatever means to calculate the quantiles. One convenient way is to use R or Excel or even some online calculators. The drawback of online calculators is that it's not all in one page, so you have to, for every distribution, you have to look for one that you are comfortable with. And also after a while, like what I've done, after a few years, then the one that you like was replaced, or when you Google it, probably it is pushed. Don't know how far it is in the Google search. So I could not find something that I find it useful. But anyway, what I'm going to say is in your examination setting, now don't worry too much because your exam is only two hours of your whole life, so shouldn't dominate your thinking. But what we are going to do, we will upload certain tables that we do our calculations. And then there will be 1 or 2 tutorial questions asking you the quantile. So just to get you used to reading the numbers from the table. But that is really not ideal. The most ideal thing is will be something like a digital examination that NUS is now pushing. During the examination, you bring your laptop. You can use whatever facility in your computer, but you will be disconnected from the internet. And so, and then you can upload your examination paper earlier, but then you can't open it because we won't tell you the password. So during the exam setting, we will tell you the password, and then you can start doing work. So I think this is a bit more realistic in that sense, but until we really move into this, so this is something that we have to live with. For example, this is the situation. Suppose the height in centimeter of a randomly selected individual has this mean and standard deviation. And so we are interested to find the probability that the height of a randomly selected individual is somewhere in the middle of this, 1 standard deviation below the mean, and then 2 standard deviations above the mean. All right, so we are interested in this. But there are situations that we are interested in the quartiles. So what is the cutoff for 25%? Below which you will be in the lowest quartile, and then the other one is 0.75, which is 75%, and above which you belong to the top 25%. So this is some of the things that we are interested. And 0.25 and 0.75 is also of interest because a lot of data analysis, this capture the middle part, 50% of the data. And so this is actually called the interquartile range, the distance between the 75% of the data and then the 25% of the data, which means that the bulk of the middle 50% is captured by these two bounds. So this sort of like represents the central tendency of your data set. So this is measuring the interquartile range. Now interquartile range will be another measure for the spread of the data or the spread of the distribution as compared against standard deviations. Standard deviations and the mean and all this are very prone to outliers. I mean, if you have a very large number, it would pull your standard deviation a whole lot. But whereas the interquartile range here is measuring the spread, and this measurement is more what we call robust against very small values or very large values. So we will look for this. So this is the table that you, at least for this slide, this is what we use. And okay. Okay. So we are interested in the 75% quantile. So we will be looking here. 75% would be here. All right. And then so the quantile would be this. All right. Okay. We will have occasions to look for 0.95 that corresponds to our 10% confidence interval, and then 975. Will be the 95% confidence interval, or in hypothesis testing, these are the critical values for your critical region or your test. So these numbers are usually more important, and in some textbook they do not give you such an elaborate table. This table is actually more, I think we created it using R, just ask R to compute it and then tabulate this, all right? And the number that we give is the Q here refers to the area of the left-hand side, so in this table. But I think the table that we are going to provide you will conform closer to the statisticians use, which will be the upper tail, all right? So when the tables are uploaded, I will go through one or two of them. So this is how the table is used. Then, of course, if you are using R, so that is fairly easy. So suppose you just want the Q is for the quantile, and then you are interested in the 75%. And if you stop it like this, then R will take it as your normal distribution is mean 0, and then with standard deviation 1. All right. Now we can actually calculate this in the next slide right away. Okay. We will do that later, but so this is, if you just input this, then this will be just the number that you see. And of course, you can provide 0, and then this is the standard deviation, but it would be the same because this would be, this is the default of this, all right? So we'll have the same number. Now, yeah. Okay, one of the things that I can remember top of my head is in a lot of IQ tests, the kind that the mean is actually 100, and a lot of calculations suggest that after they monitor the test, the standard deviation is 16, if I remember it correctly. So if you are interested in what would be the cutoff if you are among the 80%, so if your IQ test is, the score that you have is 116 or 117, you will belong to the top 20% in the IQ test, all right? Now, of course, don't take it too seriously. this kind of IQ test has been criticized by a lot of people, saying that the emphasis is more on the verbal as well as quantitative. So if you are good in this too, then you will score very well. Doesn't mean you are very smart. All right. Yes.
For the calculating the quantile, if our calculator can do it, will we be able to use that?
Yeah, good question. I mean, I wanted to address this. Since we have no restriction as for what kind of calculator you bring, so some of you using graphic calculator, and so this number will come out immediately. So to make it on a we try to level the playing field among those who don't have a graphic calculator. Then the questions are making this kind of calculations very unlikely to occur. Yeah. All right. Or we will give you a few choices where you can just pick and choose. So yeah. So if you don't really need your graphic calculator for other purposes, I would advise you not to spend the money. Right? I mean, buy some movie tickets maybe. So on a common test, the average score was 74, and the standard deviation was 7, and the grades are curved to follow a normal distribution. Find the 60 percentile. Okay. So if we are looking for the 60 percentile, so we just use Q 60 percentile. And then the average, we have to enter the average, which is 74, right? And then the standard deviation is 7. All right. So that would be 75. So if you remember, 74 is the mean, and that would be the 50 percentile. All right. And so now you want 10% above the mean, all right? So, but you remember that the normal distribution is very peak. So that is why you only need a little bit more. Then that would be the 10%. So the score actually cluster around the center, all right? Okay. Now, if you don't have this software or your graphic calculator, and the table we are going to provide you is only the standard normal. So you have to normalize this. All right. Now, this procedure seems unnecessary if you have a graphic calculator, but the thinking is actually still very important. This is what sometimes people call it set score. By subtracting your data with the data mean, and then divide back by your standard deviation. So you change it to what they call a set score and absolute values, which is independent of the unit that you are using. So that is the way to measure. One fun question that I set some time ago is, suppose you were only told that the average mark of this class is 70 marks, and you were told that you get 80 marks. So you should be happy because you are above the average. But how happy should you be, depending on the standard deviations? Now, suppose I tell you the standard deviation is 10, so you are just one standard deviation above the average. But if the standard deviation is 5, then you should be happier because you are now 2 standard deviation above the average. So the measurement is not the absolute 10 marks that you are above the average, but what are the units that you are measuring. So the unit that should be measuring is in terms of the standard deviations, and that is the unit. And that is the thinking behind of the normalization. Your x minus the mean over the standard deviation. This is measuring how much in terms of the units of standard deviation you are above or below the average. So that is still useful, even though the procedures to find the quantiles is sort of like not appealing anymore. Okay, so we have this. Yes. Sorry? Where is it? Let me, the last line. Oh, yeah, I think there is a typo. Yeah, the typo is planted to make sure you are not sleeping. So, yeah, so it is, I mean, a design of the slide, all right? But, yeah, I mean, shows that you are awake. Thank you. Okay. So, the normalization part is not necessary. So you save quite a bit of work by doing this. Okay. The width of a slot of this thing in fogging is normally distributed with this mean, and the standard deviation is this much. The specification limits was given to be plus or minus 0.005. Now, what percentage of foggings will be defective? So meaning that it would exceed this, all right, or either 0.905 or above, or 0.895 or below, right? So, so this is just looking for this. So it would be easier, just like in the way it is solved here, to find those that are acceptable, because those that are not acceptable will be the opposite of this. So, but this is now, I can calculate the one probability rather than two probabilities. So I'm computing the middle part that is within the specification. So this is how it is done, all right? And so we sort of like standardize it. We try not to call it normalize it because it might suggest the underlying distribution is normal. But this step actually, we do not require normal distributions. Only when we are coming down here that we do require that it is normally distributed. So anyway, these are just little things because the table usually only give you the positive values, will not give you the negative values. So again, you have to make use of some properties of the normal distributions. All right. Okay, so as a result, about close to 10% of foggings are defective. Okay. And now we wanted to ask the reverse problem. What is the maximum allowable value of sigma that will permit no more than 1 in 100 defectives? Now this is the, I mean, if you are in the industry of making this kind of things, this is the precisions that you should aim at. Now this is easy to ask, but whether technology can keep up with, I mean, making it so precise is another matter. So that would be an engineering or construction manufacturing problem. Okay, so what is the question is asking is, instead of the sigma is given to be plus or minus 0.005, now I have an unknown value sigma, and now this is the acceptable unit. So the defective percentage is less than 1%. So meaning that the acceptable percentage should be at least 99%. So they are equivalent statement. So and you repeat the same calculations as before. This would be a good exercise. Now you still minus 0.9, but now you replace it by why is it 0.003? Oh, okay, this is 0.003. So but now you replace it by sigma. All right, and so this number will carry a sigma in the denominator, and this will the same thing. And because of the symmetry, you still have the 2 here times the this part minus 1. So this is how it come out to be. I think it would be more consistent with the previous slide would be if you replace it by phi, the big phi of 0.005 over sigma. and then you continue to do the calculations. So we simplified this to this now, and so we are requiring this. And in other words, this is the 0.995 quantiles. All right, so this is where it is. So and this number is 2.576 from the table. All right, we can do that here. So we wanted the normal. We want 995. So this is the number here. All right. Now this is just a repeat of what I mentioned some time ago about the property of normal. The normal distribution actually are very much clustered around plus or minus 3 sigma. I'm not familiar with people in the quality control training. A lot of workshops are 6 sigma workshop, and then they charge you a few $100 or $1,000 for this kind of thing. I suppose the 6 sigma actually means plus or minus 3 sigma. So in between is from minus 3 sigma to 3 sigma, so it's 6 sigma. I'm not sure, I'm just speculating. I'm not interested in going to this kind of class. Okay, so, but the whole point is, even for 99.5, it captured within 2.576 standard deviation from the mean. So you can see the big bulk of the things are actually captured in plus or minus 3%, 3 standard deviations. So here we have to, the sigma has to go down to 0.0019. Now the original one is 0.003. So this is actually quite a substantial precision to expect from 0.003 to 0.0019. I mean, I'm not sure whether technology can keep up with this. All right. So this is how it is done. All right. Okay. Now, since you don't want to do normalization or standardization, it might be just tell R what is the mean and what is the standard deviation for part A. And so remember the probability here, the P here is always cumulative from minus infinity all the way to 0.905. All right, so so you have to subtract back the tail part from minus infinity to 0.895. Now these are the things that there is something that you need to sometimes pause when you're doing this kind of work, because if you use a lot of software, they will always give you a number. They will not tell you, I don't know how to do it in most cases. All right, so they will give you a number, but then this can be misleading, because if they what you input there or what you are the expression that you input is wrong, they would give you the corresponding answer for what you tell them to do. So this is something, I mean, of course, for particular problem, it won't happen. But in your work, if you do it many times, that is a problem. Now, I personally prefer R than Excel, especially you guys. These are no problem for you, because R is what we call scripted. In that sense, you can actually check your input. All right, but Excel, especially if you are click, and you can't really check whether you click wrong at certain step. Now, especially when you click, then it gives you an answer, and the answer seems reasonable. Then that is where the danger is, because you don't know whether you have consistently do it. Now, especially you are doing it many times. I mean, you will become tired. And you will make mistake somewhere, and you don't know where the mistake is made. But for this, the computer will take the burden from you. All right. So let X be the amount of sugar which a filling machine puts into a half a kilo packets, the actual amount of sugar filled varies from packets to packets. So this is because of some uncertainty or natural variations of this. So suppose X is of certain, this is 4 square, 4 probably should mean 4 gram in the same unit as this. So this is fairly precise, and the mu, but sometimes the machine might be miscalibrated, so it might give you a little bit more or give you a little bit less. Okay, and we want to seek mu so that less than 500 is only 2 out of 100 packets, because you don't want to, you rather to give a little bit more than give a little bit less, because if you set your machine to give exactly 500, and there will be 50% of the time less than 500. And if your customers are really weighing it, and they might think that you are you are shortchanging him, and he might sue you. All right. So you wanted to do a little bit more, and the calculation is just, well, you have to do a little bit more, but we don't want to overly excessive. So just 8 gram more is a little bit good enough. Now, but 8 gram here is, we can understand it this way. Because 500 is actually 8.2 gram less than the mean of the machine which producing. And if the machine, the standard deviation is 4, that means it's actually 500 is 2 standard deviation, roughly 2 standard deviation below the mean here. And this is pretty safe now because of the normal distribution. Okay, so we have this. And here, something similar. Now, this example is more or less a repeat of what we are calculating, but it has a little flavor that we are going, this has something to do with what we call confidence interval, in a way. So gauges are used to reject all components in which a certain dimension is not within the specification. For this particular case is 1.5 plus or minus D. So as long as it's plus or minus D, then it satisfies the specification. It is known that this measurement is normally distributed with mean 1.5, so we achieved the mean, and standard deviation is 0.2. So determine the value D such that the specifications cover 95% of the measurements. So what it means is that if you are producing these gauges according to mean 1.5 and standard deviation 0.2, and in order to meet this demand, I want it to be 95% of the time, all right? So that means 5% of your gauges will be rejected. And okay, so we want to seek D such that 1.5 is this. So now we do the standardization minus the mean, minus 1.5. So I have minus D and plus D on my left-hand side and right-hand side. And then I have to divide by the standard deviation of X, which is 0.2. So I have this. And now I can look it up for this. This is 95. And so now this between minus set to set is 0.95. So what it means is there are 2 tails. The small part and this part will combine give you 5%. So in other words, this part, because of symmetry, will only give you 2.5%. And so in other words, the lower tail would be 97.5%. All right. So if you draw it, you will be able to see. And so if you look at the 0.975 quantiles, this would be this. All right. So we can all right. So this is 1.96 is around to round this up, all right, to 1.96. And if you only need the number, round it to integer. So this is very close to 2, all right? So sometimes you can just think of it as 2 standard deviation, all right? And so D can be like this, all right? And so if D is like this, then we will guarantee we have a 95% coverage, all right? So 95% of the gauges produced will meet the standard. Okay, maybe I should stop here for a while. And now, but as a motivations, we have introduced you. Binomial is our main interest, all right? Because somehow binomial distribution pops up very often. And then I've told you that people in the past has to calculate, tabulate it. It's actually a book, all right? And now, so people are interested to approximate this. We have mentioned about the Poisson approximations. Poisson approximation is applicable when p is small, or when 1 minus p is small, because we can relabel success and failure. So meaning that when p is very close to 0 or 1, we can handle it. And now how about p that is moderate? And this is the situation. So when your probability of success is moderate, so you can't use Poisson approximations, we still have another approximation, and that is normal approximations. So let me let you have a break, and let's come back at 10:50. Okay. Now, I'm not familiar with graphic calculator. I would imagine, say, suppose your this kind of questions. Let's say example 8. Or this kind of problem A. Then using your graphic calculator is straightforward because we tell you what x that we want, and then we give you the mean and then the standard deviations. So this is just inputting the right thing into the graphic calculator. But solving it in a reverse manner with something unknown inside, then I think it probably will beat your graphic calculator because you can't enter an unknown number into your graphic calculator. So that is the kind of situations here. I think I wanted to elaborate this a little bit because I think some of you asked me. Actually, I forgot that one of you asked me at the end of last lecture, and then this question pops up again. So it might be of interest to explain it. A lot of these calculations make use of the picture and drawing it out would be helpful. So example 8, this is part B, and we are interested to find out the random variable set, which is standard normal, bounded by certain number, so that this is 0.5. All right. So what it means is this. We want a set here and then a minus set, and so that this area is 50%. All right. And so as a result, because we know everything, so I only revealed 50% just now. So anyway, the middle part is 50%. We know the total area is 100%. So this part, this lower tail as well as this upper tail will give you 50% as well. And now by symmetry of the density function, this would mean this must be 25%. Because it would have an equal split of this. Now, and so this would mean that the area on the left-hand side of the small set would be this blue shaded area plus this left tail. And so this would be the same as Z is less than or small set, the same here, the same number, all right, and would be 0.75. So this is how this is done. A similar questions pop up, I think, somehow the 0.95 thing, right? Is it example 10? Okay, so again, something similar. So this is just, it is being slightly packaged a little bit differently, but it is actually what it says is the same thing as before. So I'm interested in finding small set so that it would cover 95% of the area, and so but this is the same as this, all right, as before. And now again we draw the picture in a similar fashion, and so now we just want to exaggerate a little bit. So this will take up 95%, and since 5% will be equally split between this upper tail and this lower tail. So this much would be 2.5%. And so this number has to be the same set here, would correspond to 0.975. So this is how the explanation goes. All right, but the problem now for this little set is actually d over 0.2. So I think this kind of problem you can't use a graphic calculator. All right, so you really have to understand this. Okay, let me repeat what I just mentioned about binomial. We are interested in calculating binomial probability for a certain range or whatever. Now, you know how painful it is for when n is large. Say, if n is, say, 50. Suppose I have 50 multiple choice questions, and then I want you to calculate, suppose the p is 0.2, and I want you to calculate the probability that you will get something like 20 questions or above right. Now, no matter whether you do the opposite or not the opposite, if you use a calculator, you still have to calculate 0, 1, 2, up to 19 or up to 20. Now, you have to ensure when you are pressing the button, you get it right. One little mistake somewhere, especially the calculator gives you a sensible number, then that is where the mistake can be. Now, this is your calculator age. Imagine you don't have a calculator, and then you have to compute all this factorial. Of course, in the past, people built up this n choose k. In the West, it's called Pascal triangle. But then there is a version in the Chinese, which is much earlier by Yang Hui. So we have this. So basically calculating the binomial coefficients, if you have a big enough table, you can do that. But the pain is still multiplying this. So now when p, so this is p here, when p is very close to 0, the mean of a binomial is equal to np, and then the variance of a binomial is np 1 minus p. So when p is small, the mean is almost equal to the variance. Okay, and now the Poisson thing is integer value, also non-negative. So and the Poisson enjoys the property that the mean is exactly equal to the variance. So when you ask yourself whether Poisson is a good approximation of the binomial, the question can be translated to asking whether the mean and the variance of the binomial are very close. All right. So if that is so, then you can do it. Now when p is close to 1, we still have the trick. Because now we do it this way. Success, we call it failure. And then failure, we call it success. So over here, x is counting the number of successes. And if you change the label, you will be looking at n minus x, and we call it y. And now, so over here, it is binomial np. And now, of course, p is no longer small, but we have this is the binomial n 1 minus p. If you think of this as your new p tilde, then this p tilde is small. Okay, so in other words, as long as you are somewhere here and somewhere here, you are safe. You can use Poisson, except that when it is here, you can right away use Poisson. And when you are somewhere here, you have to do a little work to translate the success and failure in an opposite manner, and so you can deal with this. So the question remains is how about moderate p? All right, and so this is the normal approximations. Now again, even in the past, the Poisson can be troublesome without calculator, so again, people tabulate the Poisson tables for different lambda and so on and so forth. But the number of tables is much less because there is only one parameter. All right, but for binomial, you have to have tons of table because different n, different p. All right, and now the normal is even better because all you need is just one table because we translate everything into a standard normal. So we have learned previously that when n is large and p is small, we may use the Poisson approximations to Poisson distribution to approximate a binomial distributions. But when n goes to infinity and p is moderate, then we can use the normal approximations to approximate the binomial distributions. Now, in fact, even when n is small and p is not very extremely close to 0 or 1, the approximation is fairly good. Now, let me give you an intuition why this is so. Some of you must have learned or at least some exposure to central limit theorem. Central limit theorem means that when you add things up, it will be closer and closer to a bell curve. Now, if your starting point of a binomial, the p is very close to 0 or 1, the histogram is actually very skewed. When p is small, it is something like this. All right. When p is very large, it's something like this. All right. So the normal, so you will see a big contrast between. So it is definitely not symmetric. Now, but normal distribution is symmetric. So here you need n get bigger and bigger in order to first the n has to be large enough to gradually correct back the skewness, so that it would be more and more symmetrical. But when p is already quite in the middle, so the histogram of the binomial is fairly symmetrical, you don't really need a very large n. Now, so I think maybe in your high school, people give you different rule of thumb, 25 or 30 or 35. These are just guidelines. Now, in fact, if you use uniform distribution, 0, 1, even n equal to 6, if you really work it out, then it is very close to a bell curve already. So for uniform distribution, because it is already, the starting point is entirely symmetric. So when you add them up, you don't need to have a large number to correct the symmetry first. So it helps. So even when n is like 20, but your p is very much in the middle, your histogram is very symmetrical, it is actually quite good. So now what is, so the relationship between n and p is the n times p is bigger than 5, and n times 1 minus p is bigger than 5. So this inequality guarantees the p can't be too small. Okay, so this is to prevent p to be very small, meaning that your histogram is actually like this, all right? And here is actually symmetrical, the condition. It is, you see, end of the world, so we can stop here. Don't worry about your exam. So, P, because this is the failure, all right? So the number of failures basically has to be at least 5. This is the number of expected number of success has to be at least 5. Now, whether it is strictly bigger than 5 or bigger than or equal to 5, it is a rule of thumb. So, I mean, you just take it as okay. So we don't argue about whether it is strictly bigger than 5 or bigger than or equal to 5. But anyway, the point of these two conditions is to prevent p to be very small or p is very close to 1. Okay, so the normal distribution. Now, this is our usual method of standardization. The standardization is to subtract the quantity by its mean. And now since x starting point is a binomial random variable, so this is n times p. It is the mean of the binomial. And now the variance of the binomial is n times p times 1 minus p. So as a result, if you take the square root, this will be the standard deviation. So basically, everything has to be measured in terms of the unit of standard deviations away from the mean, all right? So this is the away from the mean, and then the unit that you are measuring is in terms of the standard deviations. This is approximately distributed as this. Now, I think one of the quite a number of problems that we ask you to do in next week's tutorial, because I assume that you have graphic calculator or you just use online binomial distributions or R, then you can actually calculate the actual values. So the question actually in the tutorial is outdated if I ask you for approximations, because you can actually calculate the exact values. But I think there is still values, because that's why the questions in the tutorials are, I'm asking two parts, asking you to give me the exact probability as well as give me the normal approximations, to let you have a sense that when the approximation is good or when the approximation may be bad, all right? So this is, you don't really need to remember this, because this is our normal way of standardization, is subtracting the mean so that we move the mean to 0, and then we scale everything, measure everything in terms of the standard deviation unit. Okay, so this is an example. N is 15, and then probability of success is 0.4. And now we are trying to use a normal approximation. So the normal approximation is to match the mean and match the variance, all right? So the variance of the normal is matched with the variance of the binomial. So basically, a general philosophy of trying to do approximation. This is peculiar to Poisson, normal, and in the previous one is peculiar to Poisson. But generally, we are trying to match the moment. If we can match the moments more and more, the intuition is that the approximation is better and better. So now n times p is 6, and we have 3.6. And if you really want to check n times 1 minus p, and that would be n is it 15? And then this is 15 and this is 0.6, all right? So that would be 9, so that would be fine.
How do you get 3.5?
How do I get 3.6?
3.5.
Where is the 3.5? Oh, here. Oh, okay. Yeah, this is what we call continuity corrections. Yeah, I came prepared, so. Okay, this is from the internet, all right? Okay, now basically, this is the histogram, and let's say this is the histogram comes from the binomial. So suppose this is 4. Now this is the normal curve, and I wanted to approximate this bar, this area. The reason why I'm interested in the area is because the height of this rectangle corresponds to the binomial probability at 4. Okay, this is how this number is. And then, I mean, for visual effect, we do it in this way. All right, so that we actually draw a bar to represent it, because the area of this rectangle is the same as the height, because the base is 1. So this is the So instead of approximating the height, I'm approximating the area. But when you're approximating the area, so I'm using this portion to approximate this. All right? This might be a good one because I overestimate here, but I underestimate here. So, so the two things might actually cancel out. So my approximation would be decent. All right? Is that all right? So this is the same argument. Later on, a few slides down this lecture, will be what we call continuity correction. So, okay. And so we get 12.14%, and the actual number is 12.68%. So the normal approximation has underestimated the actual probability, and now we have to understand this in terms of the relative error. So the true answer is this. This is this. So we can work out the relative error. So 0.1268 minus 0.1214. Okay, add in the 0 there. And so this is the amount that we deviate. And then divide back by, all right. So we only make about 4% error, all right? And of course, now in this case, we underestimate by 4%. Okay, so, all right. Now, this statement is relative. The approximation is not too bad because there is no very strict guideline what is good and what is bad, all right? If you are dealing with billions of dollars, 4% mistake can be a lot of money. But if you are dealing with something like a few hundred, 4% is tolerable. Okay, Barry Bonds. I have to admit my ignorance. For a little while, I thought he's talking about financial things. So, but actually, he's a baseball player. I think he's pretty famous, I suppose. Barry Bonds has a career on base percentage of 0.444. I'm not sure whether this is a good, a very decent percentage. Suppose it is. Suppose this is an accurate estimate of his probability of getting on base when he's at bat. Also assume that that each at bat is independent. Now, of course, you can argue about whether it is reasonable to assume it is independent or not independent. I mentioned a few times people in sports there is some belief of hot hands. If you are good, you have a higher percentage of getting, for example, basketball player. But there are also people who dispute that the hot hands theory. But anyway, whether it's independent, it is very difficult to argue. All right. What is the probability of Barry Bonds getting on base at least 20 times out of 50 at bats? So, so X would be counting the number of on base, or is it whatever? Okay, successful. Okay, X is counting how many times he's successful out of 50, and this is the probability of success. So. And now we are trying to check whether this is fine. This is very much exceeding 5, and so should be a good approximation. And okay, now to use normal approximation of this, we need to pin down the normal distribution. To pin down the normal distribution, we need to have the mean and the variance. All right. So n times p. Will give you the mean of the binomial, and so which is 22.2, and then the variance is NP times 1 minus P, and is 12.34. Now, generally, if the standard deviation is fairly respectable, like this, then you have some kind of assurance that it is going to work quite okay, because if this variance is very small, because when you are doing standardization, you are going to divide it by a small number, so that might magnify the discrepancy. Okay, anyway, so this is using this, and so we will have this, all right? This is using the symmetry of the normal distribution. Okay, is that all right? This is equal to this, and so this worked out to be something like 78%. So it is a very good percentage. I mean, and I think we can calculate the actual number. The actual number is 77.81. So this is remarkably close to that. So this is all because the whole thing, this is very close to 0.5. So the binomial distribution is very symmetric to start with. All right, so the approximation would be quite good. Okay, so this is how it is done in our codes. In the above calculations, we have made use of continuity corrections to improve the approximations. Okay. This, and I think it probably takes 2 slides. It's a bit long-winded, but actually the whole point is, okay, a rule of thumb is x equal to k. Then, of course, you are just looking at the one bar of the histogram. And so k, and then so your starting point should be k minus half, and then k plus half. So this you probably need to remember. But now, x bigger than 20, what does it mean? X bigger than 20 means 20, 21, 22, and so on. So the infinity part is taken care of by the approximation. But when you're looking at 20, you have to go a little bit more, 19.5, because that is where the bar is. So you have to include 19.5, all right? So, and that is why it is using 19.5 here. And so, now it's a lot of things to remember, but actually you don't need to, because here it means the set itself corresponds to x equal to k, x equal to k plus 1, and so on and so forth. So you only need to deal with the k. But when it's k, your graph, the histogram, actually go a little bit beyond k to the left, and that would be k minus 0.5, all right? And less than or equal to k, then you need a little bit on the, go beyond the k, so you need a 0.5 on the right-hand side of k. So if you really draw a rough diagram, like the one that I show you, you don't quite really need to remember this. Because if you, well, you guys probably have very good memory, but you might get confused if you just try to remember it. Now, our system is made up of 100 components, and each of which has a reliability equal to 0.9. These components function independently of one another, and the entire system functions only when at least 80 components function. What is the probability that the system functioning? Okay, so here the solution is trying to use normal approximations, and so you can check that we are safe. The condition bigger than 5 for the n times p, and n times 1 minus p is bigger than 5. It is because this is 90, n times p, so it's bigger than 5. The other one is n times q. N times p times q is already 9, So definitely n times q is bigger than 5, right? So the system is functioning if x is in this range. Now, what are the numbers that we are interested? We are interested in 80, 81 up to 100. But at 80, your histogram actually the left hand end of the bar start at 79.5. So that is why we use a 79.5. And then the bar here end at 100, but the right hand boundary of the bar is actually 105, right? 100.5. And so this is it. So we have this. All right? Okay. Let's try to rework this. Okay, so the binomial n is 100, the p is 0.9. Okay. Yep. Okay, I was thinking whether it is reasonable to use Poisson approximation. I was about to demonstrate, but now I wanted to change it to a questions. Do you think it would be sensible to use Poisson? The answer is staring at you in this line. Do you think it is a good one to use?
No.
Why?
Above 5.
What is the property of a Poisson in terms of mean and variance? They are equal. And now the underlying binomial, the mean and the variance are very unequal. Okay, so it would not be reasonable to use a Poisson to do that. Okay, so I think I will start lecture this on Friday rather than go a little bit of here. Now, I think I really like the quote here. I'm not a poet, but really this is the whole essence of sampling. You see a little bit of things and then you want to tell something about the populations. And that is the whole essence of statistics. I wanted to relate this with the difference between probability and statistics. Probability is you assume a certain way of operations. So but then you are interested in a certain situation. One example would be like a chess game. And you have a very strict rules of how to play. And now if you play in a random fashion, you will be able to see certain method of playing. You will have a higher probability of winning. And certain kind of playing, you will have a lower probability of winning. So this will be probability. But then on the other hand, if I show you the middle of a certain chess game, and you wanted to reconstruct back how the game was actually played, this is almost like the reverse of this. So in some way, this is closer to statistics. So you want to, you observe certain things, and then you wanted to understand how these things arises. All right. Now, talking about this, the chess game, it is really powerful. You have heard of the AlphaGo thing. At the beginning, the AlphaGo, as far as I know, they come up with a program and then they have to play with the expert. So I was told about 200,000 chess record among the top players is available. So to train the AlphaGo, they let the program to play with these top-notch players. But still not enough to train it. So I think the AlphaGo at that time used the best chess software at that time, and then let AlphaGo and play with this top software millions of times. All right, and so finally it defeats one of the best chess Go player, the Korean guy. What is really stunning, later on, AlphaGo actually came up with something even more stunning, because we always think that when you learn things, you want to learn from the expert, and then you will improve. But what really surprised us is that AlphaGo come up with a newer version. They don't even need to play with the expert. They just play against one another. The AlphaGo play against itself. Now, and then after playing 3 days, they are able to reach the expert level. Now, this kind of problem, of course, the inventor of the AlphaGo, make a bold statement. From now on, we can use AlphaGo or the similar thinking of deep learning to solve political problem, economic problem, and so on. But I think this is really far-fetched. One of the things that AlphaGo is capable to do is because there is a very strict rule of determining who is winning and who is losing. I think that is the feedback that is the AlphaGo is able to learn. The AlphaGo can keep on playing, but at the end of the game, there is a feedback telling that this game you lose or this game you win, and that is how he gained the experience. But in other situations, you can't really define what is winning and what is losing in a very definite way. Then I think this still needs to be improved. All right, so maybe we stop here. Now, one of the things that later on we are interested in the sample size of certain survey or certain other things. We probably won't do a lot here, but this is a problem that a lot of experimental scientists need to address, because especially if the experiments involve money and also resources. I was once asked, a little bit gross, a graduate student from dentistry asked me this, because they have to pull out the canine tooth of a dog. So they don't want to pull out too many. So that is, but they would also want to do the experiment in a satisfactory conclusion. So they have to find out, how many canine teeth do they have to collect. Now, of course, if they only need 10, and I tell them 100, then of course a lot of dogs will be suffering. Okay, so you have to be precise in certain way. This does probably cost money as well as, but cause a lot of pain to your pet. All right. So maybe I'll stop here, and then we'll talk about this. We'll be moving more like towards statistics now. Yes.
Will you upload next week's tutorial today?
I can do that. Yeah, I can. Tutorial 9. Okay. Yeah. I thought I have uploaded it. I haven't, right? Oh, okay.